We can also use definite integrals to find the areas of planar regions that are bounded by several curves, and the curves intersect. So in this case, to find the area of both of these regions, we can use a piecewise integral. And if we designate this function f of x and this one as g of x, and the thickness of each rectangle dx, then the area of the first region is f of x minus g of x, which is the height of one rectangle, and then multiplying by dx gives us the area of that rectangle. And then we integrate from x equals a to x equals b, and that gives us the area of that first region. And similarly for that second region, we integrate from b to c, but this time the height of each rectangle is g of x minus f of x, to give us a positive height for that rectangle, which we integrate with respect to x. And that gives us the area of the second region. And sometimes you have to use some algebra to find the coordinates of that intersection point, which we'll do in the coming examples. Let's find the area of the region bounded by the parabolic curve and the square root curve over the interval from 0 to 2. And we're asked to use rectangles perpendicular to the horizontal axes. So these are going to be vertical rectangles with an infinitesimal thickness dx. So from the interval from 0 to 1, the square root curve lies above the parabolic curve. So we subtract x squared from x to the 1/2 to obtain the height of that rectangle, and we integrate from x equals 0 to x equals 1. Now for the interval from 1 to 2, the parabolic curve lies above the square root curve, so we subtract x to the 1/2 from x squared to get the height of that rectangle, and then multiply by the infinitesimal thickness dx, and integrate from 1 to 2 to obtain the area of that second region. And evaluate these integrals, and post your answer in the comments. Let's find the area of the region bounded by these two curves over the interval from 0 to 2, and use rectangles that are parallel to the x-axis. So because we're using horizontal rectangles, we're going to integrate with respect to y. And we need to break this up into 3 regions because we have an intersection point, and the integrand is going to change between the second and third regions. So have a think about that. So because we're integrating with respect to y, we're going to write the equation for the parabolic curve in terms of y, and the equation for the square root curve also in terms of y. Now for this first region, the parabolic curve lies to the right of the square root curve, so we subtract y squared to get the width of that rectangle, and then integrate from y equals 0 to y equals 1 to obtain the area of that region. Now to obtain the area of the second region, we're going to integrate from y equals 1 to the top of that second region, which is given by this equation, so y is equal to root 2. And to obtain the width of that rectangle, we have the square root curve lying to the right of the parabolic curve, so we have y squared minus y to the 1/2, and we evaluate the integral over y. And I'll leave it for you to construct the integral for the third region, and then calculate the area and post your answer in the comments. Let's find the area of the region between these two curves. So for the first curve, it looks like a parabola. And for the second curve, if we set x equals 2, y equals 0, and if we set x equals 1, both curves pass through the point 1, 1. So therefore this is an intersection point. And if we set x equals 0, then y equals 2 to the quarter, which is around 1.2. And if you take the derivative, it's going to approach infinity as x approaches 2. So the curve's going to look something like this. And therefore, to avoid evaluating this integral piecewise, we're going to take horizontal rectangles. So the thickness of the rectangle is dy, and we thereby need to write the equations for these curves in terms of y. So we get y to the 2/3, and x equals 2 minus y to the 4. And then to get the length of that rectangle, we can subtract y to the 2/3 from 2 minus y to the 4. Then integrating from y equals 0 to that intersection point, we obtain the area of the region. So evaluate the integral and post your answer in the comments.